Okay, so I'm going to split this video into two parts. Hopefully neither part should be terribly long. This is section 7.5. We're going to start out talking about the integral test, which is another test to decide if a sequence, or rather a series, is convergent or divergent. Here's how it works. If suppose you have a series, okay, and you can define that the sequence that we're summing as a function. Okay. So the example we're going to work with is this series here, where we start with n equals 1 and we go to n equals 2 and equals 3. Well, this is a well-defined function if I let the value here take on any value, as long as x is positive or bigger than or equal to 1. So this is a function because it includes all real numbers bigger than or equal to 1. This only deals with integers or natural numbers. Okay. So if I can do that, then what we're saying is that if I consider the integral from 1 to infinity, so this is a continuous function, dx, from 1 to infinity, if the integral, the improper integral from 1 to infinity converges, then so does the series. If this diverges, then again, so does the series. That's a pretty simple concept. So basically, if you can rewrite it as an improper integral, then, and you can test this, you can find out whether or not this converges or diverges. It does not tell you what the value of this is going to be. It only tells you whether or not it has a finite value. Let's look at a bit of a proof here. Okay, I'm going to sketch the proof for you. We're not actually going to go through it, but give you an idea. Here is the function 1 over x squared. Okay. And what I want to do here is I want to look at the Riemann sums. So if I look at the integral from 1 to infinity, the improper integral, then I'm looking at the area from 1 all the way to, I'm looking at this area. That's the area. That's the integral. But remember, the way that we compute area is with a Riemann sum. Okay. So the Riemann sum is going to look like this. There's two ways I can do it. And remember, I'm really only interested in the integer value. So I'm going to look at my Riemann sums are all going to start over here somewhere, and they're all going to have a width, a delta x equal to 1. Because I'm not going to consider any other Riemann sums. Just a left-hand Riemann sum and a right-hand Riemann sum with delta being 1. So the distance of every interval. So there's two ways I can do this. I can do the left-hand Riemann sum, which notice is an overestimation. Okay. So we have the left-hand Riemann sum is going to look like this. N equals 1 to infinity of 1 over n squared. Okay, we're going from 1 times 1, 2 times 1, 3 times 1, 4, and so on. So that's going to be this is the left-hand Riemann sum, and it is larger. It's an overestimation of the integral from 1 to infinity of f of x. Pardon me, we have an actual value here. F of 1 over x squared dx. Okay. If we look at the right-hand Riemann sum, I'm going to do the right-hand Riemann sum in another color. We'll do it in red. If I look at the right-hand Riemann sum, that's starting here, here, here. Notice the right-hand Riemann sum is an underestimation. And that's because this function is decreasing, strictly decreasing. So what that means, and I'll go back to black here, is that the right-hand Riemann sum, which is really the exact same thing as this, except we start at 2. Now we go 2 times 1. 3 times 1. So right, if we start at 2 and go to infinity, the right-hand Riemann sum is always going to be an underestimation. Okay, so what that means is anytime I look at an integral, I can always bound it by the right-hand Riemann sum and the left-hand Riemann sum. The integral, remember, is always going to be bounded by those two values. Now, in this particular instance, the right-hand Riemann sum is less than the left-hand Riemann sum, but it doesn't always have to be that way. No matter what your integral is, the right-hand Riemann sum and left-hand Riemann sum, one will be an overestimation, one will be an underestimation. It is possible that they're equal, in which case it's even better. Okay, so we have a boundedness here. So let's look at the logic here. Let's look and see what would happen to the left-hand or the right-hand Riemann sum if this were convergent. So if we were to calculate this, the actual integral, and find out it converges, that means this goes to a number called L. Well, if this goes to a number, since this is bigger than this Riemann sum, this also must go to a number. We'll call that m. How's that? Okay. Okay, so that means that the lesser one must go to a number since it's bounded above by an actual number. Well, this is bounded by, this is a number, but look, the only difference between the left-hand Riemann sum, pardon me, the right-hand Riemann sum, and the left-hand Riemann sum is one term. And in these particular cases, that's always going to be the fact of the matter. The only difference here is one term. The only difference between the right-hand Riemann sum and the left-hand Riemann sum is one number, the first term. So if this goes to a number, if this converges, that makes the other one converge. So if the middle converges, both the left and the right Riemann sums converge, and lo and behold, this is the sum we were talking about to begin with. So the left-hand Riemann sum is always going to be the sum we're interested in, and if the middle part of the inequality converges, it forces the right-hand Riemann sum to converge, and therefore my original sum to converge. Okay, so that's why if this converges, then the two outside converge, and therefore my original sum converges. It doesn't say to what it converges to, but it says it converges. Well, let's see here. What would happen then if the middle one diverged? So what if the middle one here, the integral, diverges? What happens if it goes to infinity? Okay, so what's going to happen if this goes to infinity? Well, if this goes to infinity, remember this is less than this Riemann sum. So if this goes to infinity, that forces the value that's bigger than it to also go to infinity. But remember again that the upper and the lower are only different by one number. So that means that if this goes to infinity, then so does the lower. Okay? So if the middle goes to infinity, they all go to infinity. If the middle goes to a number, they all go to a number. And that we can look back now at our original one here that says that, look, if the integral converges, the sum converges. If the integral diverges, the sum diverges. Okay, so let's just look at a real simple one, the one we were just looking at. Let's solve this particular integral and just make sure that we have a sense of how this is going to work. So we want to know, does this converge or diverge? So we look at the integral 1 over x squared dx, and remember this may converge. It doesn't necessarily diverge because this goes to 0. That's the divergence test. Well, this is the limit as b goes to infinity of 1 to b of 1 over x squared dx. This is going to end up being the limit as b goes to infinity of negative 1 over x from 1 to b. You can check that, right? This is x to the negative 2. The antiderivative of x to the negative 2 is x to the negative 1 over negative 1. Okay. So the limit as b goes to infinity of, put in a b, we get negative 1 over b plus 1. So this goes to 1. So since the integral converges to the number 1, the sum converges. We don't know what it converges to, but we know it converges. Very nice. Okay, so here's some other applications. This is a very important one. That's the question, does the harmonic series, this is called the harmonic series, just 1 over n, does it converge or diverge? So, does this converge or does it diverge? Again, let's take a look at the integral test. First of all, the divergence test says it might. It might converge because this goes to 0. So this going to 0 means it may converge. Doesn't necessarily though. So let's check the integral. 1 to b, the limit as b goes to infinity. Now I could have written the first part, right? 1 to infinity, but I just skipped that for now. 1 over x dx. Well, the antiderivative of 1 over x is ln. So the limit as b goes to infinity of ln of x from 1 to b. This is the limit as b goes to infinity of ln of b minus ln of 1 is 0. Ln is an increasing function, so as I let b get large, this goes to infinity, which means that since this integral diverges, so does this series. The harmonic series diverges. Okay, really important, kind of fascinating point. Okay, back to our slideshow. The last one I want to look at for now in this particular section is going to be this problem here. And this is a particular problem we want to figure out, is this going to converge or diverge? This particular series here. And again, I don't have any sense of it, so let's just try it. This goes to 0, which means the series might converge. The divergence test doesn't do anything for us here. All it says is that this might converge, it might not. But one other thing we can do is the integral test. 1 to infinity of 1 over 2 root x, times root x plus 1 dx. So if this converges, then so does this. And if this diverges, then so does this. Okay, we're going to do a u substitution, let u equal root x plus 1. That makes du equal to 1 over 2 root x dx. Now if we plug in u in here, we're going to see this is going to be 1 over u, and this will cancel out. So we'll end up with an integral of 1 over u du. And I'm leaving the integrals off, limits of integration off right now until I do my u substitution back in. This is ln of u. Okay. Evaluated from some number to some number. I'm leaving those blank for now. But u is, ln of u is going to be root x plus 1, and I'm evaluating this from 1 to b. Okay, so let's move down here. This is equal to the limit as b goes to infinity of ln, the absolute value of x plus 1. Now we don't really need the absolute value here because this will always be positive, but that's all right, from 1 to b. So again, I have the limit as b goes to infinity of ln root b plus 1 minus ln of 2. Now this is finite, that's fine. This part, however, root b is increasing. Okay, root b, remember, is this function. So this is increasing. ln is also increasing at, again, a similar kind of rate. So ln is increasing. Root b plus 1 is increasing. That makes this always increasing, which means this goes to infinity, which means the integral diverges, and so does the sum. Okay. All right. So this brings us to an interesting point. We've so far seen how this can apply to the situation of something like 1 over x squared, or sorry, 1 over n squared, or 1 over root x, or 1 over x. We've seen how it applies to 1 over that sort of thing. So we want to look at a general sequence here. The general sequence we want to look at is the sequence 1 over, I'll write it out this way you can see it a little different notation, n to a power. Okay. So for instance, we've looked at 1 over n, we've looked at 1 over n squared, we've looked at 1 over root 2 root x plus 1. We've looked at these different things where we have, these are n's, series with 1 in the numerator, or a constant in the numerator, and n to a power in the denominator. And we call this a p series just because this is the typical exponent we use in these cases, is p. And here's the rule. These will converge as long as p is strictly bigger than 1, and will diverge if p is less than or equal to 1. Okay? And we can do this, we might leave this as an exercise, we can do this by checking to see what's going to happen with this function. I'll make a quick argument about why this will converge if p is strictly bigger than 1, and why it will diverge if p is less than 1. Okay, less than or equal to 1. We already saw what happens when p is equal to 1. We know that diverges. Okay, because what ends up happening is taking the integral, is taking the antiderivative of ln if p is equal to 1. If p is bigger than 1, you use the power rule, and if p is less than 1, you also use the power rule. Okay, so you have to think about what's going to happen if I use the power rule on this is x to the negative p. What happens if I use the power rule on a positive exponent versus the power rule on a negative exponent? What does that create? And then when you take the limit of that, what happens? Okay, so that's going to be the crux of how this works. But all we need to know really in practice is that if I have 1 over n to a power, then it's going to converge as long as that power is bigger than 1, and diverge if it's 1 or less. Okay, so that's the first part of the video, and we'll look at the second part in a minute.